Hi everyone, we are talking tonight about the Unit 6 Day 2 notes on polynomial functions of higher degrees. So we kind of have defined already what a polynomial looks like. This should be a review. We talked about how polynomials all have certain characteristics in common, one of which is their graphs are all continuous and smooth, meaning we can draw them without having to pick up our pencil or a pen from our paper, and there are no sharp corners or this is called a cusp in them. They're always going to be kind of this smooth curve shape. The one it's not really exception to it, but we don't think of first degree polynomials as being curves because they're lines, but they are smooth and continuous just like all the other polynomial graphs. We also talked about how polynomials can be classified by degrees, and we said that a constant term, meaning no variables, is a degree of 0. Linear is a first degree, quadratic second degree, and we went all the way up through fifth degree, but really polynomials can be any degree as long as it's a whole number. And all even degreed polynomials have further behaviors in common. So if your degree is an even number, the parent function is always going to be above or equal to 0, like this quadratic. So it's going to have the same basic U shape or be symmetric on left to right, on the left to the right. And the only difference is that as this number increases, the graph kind of flattens out closer and closer to the bottom. So x to the 6th would look very similar to x to the 4th, except it would be even flatter than this graph. And x to the 8th, x to the 10th, and so on and so forth. So as this degree gets bigger, although it has to stay even for it to have this left-right symmetry, it's going to flatten out more and more. But all even degreed functions will have that kind of parabola shape. All odd degree functions kind of look similar. They have this wiggle sort of shape to them, or they have this symmetry around the origin. So basically what happens is the left and the right are kind of reflections across the x-axis, so to speak. So the same thing happens here. As the degree increases, though it has to stay odd, it also tends to flatten out closer to the origin. So this actually kind of does it gives us some interesting information. So anything with an even degree, its end behavior is going to match. And by end behavior, what I mean is what it does on the ends of the graphs, on the left side and on the right side. So all even degreed functions are going to match their end behaviors on the left and right. So this one's going to go on the left, we go to positive infinity, and on the right, we go to positive infinity, or they continue to go up and go up on the left and right. That's going to happen anytime you have an even degreed function. Even if you have a reflection, so let's say we flip this upside down, the end behavior will still match. They'll just go on both sides to negative infinity or go down on both sides infinitely. And that's going to be true for any even degreed function. Any odd degree function is going to have opposite end behavior. So we're going to start down at negative infinity and end on the right up at positive infinity. And again, even if we were to reflect that, we would just start up at positive infinity and end down at negative infinity. So the only thing that we need to determine end behavior is the degree of the function. That will tell us whether it's matching or whether it's opposite, and the sign of the leading coefficient, because that's what dictates a reflection. So if it's positive and it's an even, our end behavior will be up, up. If it's positive and it's odd, our end behavior will always be down, up. If we have a negative leading coefficient and it's positive, it'll match, it'll be down, down. And if we have a negative leading coefficient and an odd degree, it will be up, down. Another characteristic of polynomial graphs are things called turning points. Turning points are also known as local or relative minima or maxima because they're highest and lowest points, at least within that section of the graph. So for example, based on this picture here, this graph does go down infinitely on the left and the right side, but this is the lowest point relative to this area, so we would call this a relative or a local minimum, and these are relative or local maximas. This one happens to be a relative maximum because it's not the highest point, but this is also the absolute maximum because that's the highest point of the graph. When we talked about parabolas specifically, we refer to these points as the vertices or the vertex. But now because we have higher degrees, we could have more than one maximum or minimum, or also known as turning points. We call them turning points because they are the points at which we change directions. So for example, here we're going up, 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 up. We hit this local maximum and then we start going down. We hit the local minimum and we start going back up again. We hit the local maximum and we start coming back down again. So these points are also known as turning points. You are always going to have fewer turning points than your degree. So you don't always know how many turning points you have, but the maximum number of turning points you could have would always be one less than whatever your degree is. So for example, if you're a 4th degree polynomial, then you will have at most 3 turning points. Okay, so that's all that this is saying. Here we see an example of a 4th degree polynomial that has 3 turning points, one here, one here, and one here, but this is also a 4th degree and it only has 1 turning point. So it could have as many as 3, no more than 3, but it could have fewer than that as well. The last concept we're going to talk about in these notes are referred to solving polynomials. So remember that solving polynomials or finding solutions to polynomials are also known as roots or zeros, and graphically it's where the graph crosses or touches the x-axis, so known as the x-intercepts. The method that we use for solving polynomials is going to depend on the polynomial itself and specifically its degree. We learned that we can solve linear polynomials just by setting them equal to 0 and solving for x. Quadratics, we do the same way, although we can't always solve for x with a quadratic without doing something like factoring first. So factoring is a method that we have for solving quadratics. Square roots is a method we talked about in class. The quadratic formula works specifically for quadratics. And I think that's, completing the square, although we didn't have to talk about that one a lot. As we talk today about higher degree polynomials, we're going to have other methods that we're going to use for solving. And specifically, we're going to use our graph to get us started off with solving, or by factoring. So we know how to solve, or we know how to factor certain polynomials that have a higher degree, like sums and differences of cubes, as well as quadratic lookalikes. So we'll be using that specifically to solve, as well as our ability to graph it will help us find our x-intercepts as well. What's important to keep in mind in this unit about factors is that factoring something will give you the roots or the solutions because you set each factor equal to 0 and solve. So for example, if you factor something and you get x minus 3 as one of your factors, then that means that x equals 3 or positive 3 is a root or a 0 of that solution. Finally, the last concept we're going to talk about is the multiplicity of a root. The multiplicity is the number of times that a factor appears or exists in our polynomial. So for example, if we factor a polynomial and we get these different factors, the exponent, or the number of times that that factor appears, is its multiplicity. Now the multiplicity is interesting because it also gives us information about the graph. So at this x-intercept, x equals 5, we have a multiplicity of 3, which makes that x-intercept behave as if it were a 3rd degree polynomial right at that 0. So if you were to zoom in on the graph just at that x-intercept, it would look like a cubic in that little snapshot. For this one, x plus 7, it only appears one time, so it has just a multiplicity of 1. In fact, we don't even state it. At this 0, x equals negative 7, it's going to look just like a line. If you were to zoom in on the graph just where it crosses at x equals negative 7, it would look just like a line. It's just going to shoot right through. And this multiplicity of 2 at x equals positive 1 is going to bounce off of it like a quadratic would, like a parabola. So that's interesting. Multiplicity is important because it gives us information about our graph. So again, here's the information written out. Multiplicity is the exponent of the factor of your polynomial in factored form, or it's the number of times that your solution appears as an answer. Anything with an even multiplicity is going to bounce off the x-axis, and anything with an odd multiplicity will cross it, and the specific number of the multiplicity will make the behavior at that x-intercept behave as if it were like a little mini polynomial of that same degree. So here's a picture of a random polynomial that's been graphed. We have an x-intercept at 2, and do you see how right here, if we were just to look at this, it looks like it's bouncing off like a quadratic? We could tell from the graph that this has a multiplicity of 2. We have another x-intercept here at 4, and you see how this looks like a wiggle. It's not shooting through just like a line. It's making a wiggle. So we definitely have an odd multiplicity that's bigger than 1. It looks like maybe a multiplicity of 5, but for sure at least 3. But the multiplicity gives us information like that about our graph, and it gives us some information about our polynomial as well. So anyway, come with your questions. I'm sure that you have some. There was a lot of information in this video, and I appreciate you watching it. And if you've hung in there and you're still watching this video and you would like to receive some extra credit for watching this video, you need to email me with one of two things: either something that you learned and understood from the video, or one question that this video brought up. Email me that information and you will get extra credit for watching this video. Thank you so much, and I'll see you guys in class.